Alrighty, well, so we're in, whoops, not sure what's going, oh, quit that. Okay, sorry about that. So, section 5.1, we want to look at properties of the natural logarithm of x. And now, some things we've, of course, already seen is, the derivative of the natural log of x with respect to x is 1 over x. And so that means the second derivative of the natural log of x with respect to x, well, that's just the derivative of 1 over x with respect to x, which we know as negative 1 over x squared. Now, notice this is always less than 0 for x, well, for all x not equal to 0, but in particular, for x, oh, I must be, I was hitting that little button again. That's what's going on. X greater than 0. And that's our domain. Again, since we define our function, natural log of x, integral from 1 to x of 1 over s ds, then 1 over s is not defined at 0, and so we cannot, since it's an a definite integral antiderivative thing, we can't go past to the left 0. So as we look at this thing, this definite integral, those areas are all defined. If we interpret it as area, those areas are all defined as long as x is greater than 0. So we can do this. Okay, so with that second derivative, then that we see, and the first derivative, x, this is always greater than 0 as long as x is positive. And so we saw the graph already in Desmos, but this tells us that natural log of x is increasing and concave down for its domain x greater than 0. Okay, so there we're starting with some properties. Now we have all these algebraic properties that they mention. One, the natural log of 1 is 0. Well, that's easy enough to prove, because the natural log of 1, just right up here from our definition, is the integral from 1 to 1 of 1 over s ds. And, well, that's 0, because those limits are the same. Okay, 2. And theoretically, we know all these properties. And so, this shouldn't be news, but the proofs maybe are more newsy. And so in this case, in order to prove that natural log of a times b is natural log of a plus natural log of b, what the book does, and the authors do, and I think this is a really nice way to look at it, is they take the function log of ax and they take its derivative. Okay, the derivative of that, well, it is the derivative of natural log, 1 over ax, and then times the derivative of what was inside, so a. But 1 over ax times a, well, that's just 1 over x. Okay. Now, if we take the derivative of the natural log of a plus the natural log of x with respect to x, well, derivative of the natural log of a is 0, because that's a constant, plus 1 over x. And so we get 1 over x. So these two functions both have the same derivative. Well, that means they are the same function, at least up to a constant. And so what that tells us, well, actually I put it over here, is, from these two things having the same derivative, we know that natural log of ax is equal to the natural log of a, whoops, gotta quit hitting that button, natural log of a plus the natural log of x plus some arbitrary constant. Okay, now we could find that constant just by choosing some values of x. Well, if we let x equal 1, then natural log of a has to be the natural log of a plus the natural log of 1 plus c. No, but the natural log of 1 is 0. And so we get that the natural log of a equals the natural log of a plus c. Oh, well, then c has to be 0. So these are indeed the same thing. So we get that. 3. In 3, we see our nifty logarithm rule that the log of a to the n is the same thing as n times natural log of a. Okay, so we have that, and we use that same idea for the proof. And I'm getting to the end of a page, and I'm not sure how to find a new page on here. It might be this thing over there, so we'll try it. Okay, so again, let's look at natural log of x to the n. Then if I take that derivative, that again, that's 1 over x to the n, because of the derivative of natural log, and then times nx to the n minus 1, because we need the derivative of what's inside there. And so this simplifies to be n over x. Okay, but if we take the derivative of n log of x with respect to x, we get that same thing, n times 1 over x, or n over x. So once again, they're the same, and they just differ by a constant. And again, what we can do is let x equal 1, and we will determine that that constant, once again, is 0. Okay, let me see if I can make a new page here. Nope, that's background settings. Okay, so I don't know how to make a new page, and so the best thing I can come up with is maybe we'll try it this way. I think I'll have to let's see. Oh wait, I still have more room. Silly me. Okay, so I'll keep going. Sorry about that. Like I say, new tablet, new software, trying to figure it all out. Okay, so we'll try that with our, we have natural log of 1 to the n we know that that is equal to n times natural log of 1 plus an arbitrary constant. But 1 to the n is 1, natural log of 1 is 0, so we get 0 equals 0 plus c. So once again, c must be 0. Okay, and there we go. We've got that one. And the fourth property, well, there we go. The fourth property is that the log of a over b is equal to the log of a times, whoops, I think I'm doing the proof, not the, yeah, sorry. Okay, whoops. Not sure what I did. Okay, there'll be probably a lot of that. Okay, this is, oh, there's this ribbon on the bottom. I'm not sure how to, whoa, that's not a good thing. Okay, yeah, I'm not sure what I'm hitting to make that happen. So this is the log of A minus the log of B. And so, again, the proof here, actually, we don't need derivatives because we can write this as natural log of A times B to the negative 1. But then we know that's the natural log of A plus the natural log of B to the negative 1. And so then that's the natural log of A plus negative 1 times natural log of B. And so finally we get our natural log of A minus the natural log of B. Okay, so there are algebraic properties of all this stuff. And so we'll call that one done.